Let's look at a more advanced example of a heat capacity type problem. So here's our problem. A 15.00 gram iron block is dropped into a beaker containing 100.0 grams of water at 20.00 degrees Celsius. At equilibrium, the temperature of the water was 22.00 degrees. What was the initial temperature of the block? Alright, so here's a picture of what's happening. We've got a block of iron, 15.00 grams, at an unknown temperature. We're going to drop it into water. What's going to happen is that the temperature of the block is going to go down and the temperature of the water is going to increase. And at some point the temperature of the water will increase to 22.00 degrees Celsius. Here are the things we know if we assume that no heat is lost to the surroundings. First of all, the iron block will release heat to the water and the water will gain that exact amount of heat. Secondly, the final or equilibrium temperature of the water and the iron block are going to be the same. So what that means is if the water has a 22.00 degrees Celsius temperature, then the iron block will also have that exact same temperature at equilibrium. Now when I say equilibrium, what I'm talking about is that initially the water was 20.0 degrees, the iron was some temperature that was going to be higher. We don't know what temperature yet, but we do know that the iron will release its heat and will go down in temperature while the water goes up in temperature, and at some point those temperatures will be the same, and that's what I'm talking about with equilibrium. And that's what I'm saying here, is that the iron block is releasing a certain amount of heat, and it's that heat that's being absorbed by the water. Alright, so let's see how we would handle the problem. We're going to use our heat capacity equation that we've been talking about. Alright, so there's our problem. Let's go through and see how we would solve it. Now what we have, what we're after is the temperature of the block, which is what we're missing. We're missing the temperature of the block, and the block is the iron. We've given the heat capacities of the water and the iron here as well. I think a good tip with these kinds of problems is to always start with whatever you have the most information about. As you can see, we've got a lot of information about the water. We just don't have very much information about the block. So it's natural to start off with the amount of, to find the amount of heat that would be absorbed by the water. And we can do that because we've got the final and initial temperatures of the water. We also have the heat capacity. We also have the mass of the water. So what that means is I can do this. I can say Q of water equals M of water times C of water times delta T of water. That's going to be the mass, which is 100.0 grams, times the heat capacity, notice I'm always using units here with all my calculations, so I can see how everything cancels at the end. Now the change in temperature is going to be 2.00 degrees Celsius. You'll notice that when I consider a change in temperature, I don't worry about positive or negative. I'm only interested in the actual change, the difference between them. It's sort of like an absolute value, so that I can just figure out what the delta is, not so much whether it's positive or negative. And then that's going to give me 836 joules. Alright, so what does this represent? This represents the fact that 836 joules of energy was absorbed by the water, because that's what caused the 2-degree increase in the 100 gram sample of water that we have. Where did the 836 joules come from? It came from the iron block when it was placed in the water. So the iron block must have been hotter, pretty hot, and went in the water and released that much heat in order to bring the temperature of the water up by 2 degrees Celsius. Right, so that's the first part. We know now that the Q of the water, or the heat absorbed by the water, is going to be equal to the heat released by the iron. That was one of the things we had said earlier. Right, so QFE equals MFE, CFE, and delta T FE. Now if you remember what we're looking for here, it says what was the initial temperature of the block. Well, that means we're after delta T. We have the QFE, we have the mass of iron, and we have the heat capacity of iron. So for delta T of iron is going to be QFE over MFE times CFE. Now the Q is 836 joules. The mass is 15.00 grams. And the heat capacity is 0.449 joules per gram per degree Celsius. So for change in temperature now, you see that the joules will cancel, the grams will cancel, and the degrees Celsius will be on top now. And that comes out to be 124 degrees. So what does this represent? This represents the change in temperature of the iron. Alright, so now we can figure out what the initial temperature of the block was. We know what the final temperature of the iron is. The final temperature of the iron is 22.00 degrees Celsius. Now I know that because the final temperature of the water was 22.00 degrees Celsius. And one of our assumptions is that at equilibrium, the temperature of the iron and the temperature of the water are going to be the same. So what we've got to do is we've got to figure out what the initial temperature of the iron was. Now, as we know, the temperature of the water went up. So what must have happened is that the temperature of the iron must have gone down, which means that if this was the final temperature of the iron, the initial temperature would have been this plus whatever the change in the temperature of the iron was, which was 124 degrees Celsius. So the initial temperature of the iron will be the iron is 22.00 degrees Celsius plus 124 degrees, which is going to come out to be 146 degrees Celsius. Alright, so let me just sort of go through and summarize what I did here. First of all, what I did was I figured out the amount of heat that was absorbed by the water. Now I know this heat was absorbed because the temperature of the water went up, and it went up by 2.00 degrees Celsius. Now the heat, 836 joules, was released by the iron. That's how I know that the temperature went down initially, because this heat was released, and it went down by 124 degrees Celsius. Now since this is the final temperature of 22.00 degrees Celsius, I know my initial temperature must have been higher. So it makes sense that if the temperature of the iron was 146 degrees Celsius initially, that it went down once it was put in the water, and it went down to 22.00 degrees Celsius, and it went down by 124 degrees Celsius. Now, one other observation I want to make here is that you'll notice that the temperature of the water did not change very much, and that is in large part due to its very large heat capacity. It takes a lot of energy to raise 1 gram of water by 1 degree Celsius, and you can see that despite the fact that we have a lesser amount of iron you can see that the iron actually went down by a very large amount. 124 degrees Celsius was cooled, and only 2 degrees went up by the water. So you can see that the heat capacity makes a large difference, as well as the mass, but the heat capacity here is really telling. It's an observation that we can make in our own kitchens as well. If you put a metal spoon on an iron hot plate, you'll notice it heats up pretty quickly because it has a small heat capacity. But it seems like when we put water on a stove to boil, it takes forever to heat up, and that's because of its high heat capacity.